hybrid meeting, so it's very interesting in that case. I'm also I'm a faculty at the Tel Aviv University, and also a visiting faculty at IIT Hadas in chemical engineering, working there with Professor Rajneesh Kumar. And also, I can say I came to India during my sabbatical, and I think the pandemic was the longest time that I haven't came to India. I'm already here for 2 months, and I'm returning in a few days back to my home country, to Israel. But I'm returning back on January. We have the IUVA conference, the International Water Association conference. And maybe on November, because there's a huge water expo, so maybe I'll return back then. And I have a continue research with India, and this goes back for a few years. I'm working also with Tapal University on agriculture irrigation in the north, down to Amrita University, working on developing tools to provide safe water to rural areas, so all across India. And I hope that this is a start also for working with Anna University. So actually, I know it's just across the street, but this is my first time here, although I've been in Chennai for almost a year, here and there. So I'm happy to be here. Thank you for the invitation, and I will start my presentation. I would like to talk a little bit about UV disinfection and why UV disinfection can actually solve many problems related to water safety. Okay, so this is what I want to talk about. I would like to first present the International Ultraviolet Association, which is actually a forum that aims to implement UV disinfection. It has more than 700 members. By the way, the numbers are increasing rapidly all the time. If you're interested to read about the UV disinfection, we have scientists, vendors, utilities, regulators, consultants, and end users within the IUVA. We have many activities such as World Congress, symposiums, regional conferences, webinars, and we also have UV Solution Journal. So if you're interested to read about UV, you can just join. It's an access-free journal. We have partnerships with regulators all around the world, and also in the U.S. with the Environmental Protection Agency, also with ASHA and all that, and all these huge organizations such as the WRF. We also have various task forces that relate to air and surface disinfection, UV for biofouling control, industrial water, FAR UVC, UV Sustainable Development Goals, which I'll talk a little bit about that also, UV and healthcare, food, and UV LEDs. In addition to that, we have the regional UV zones. So for example, there is the IUVA Asia, which definitely I think India can join in. Currently it's Singapore, Tokyo, Bangkok, Japan. I would like to talk also just a bit before I start my presentation on the IUVA UN Sustainable Development Goal Task Force. So what is our goal? Our goal is actually to show how UV can be a solution for many issues that are related to safe water, as has been determined by the United Nations SDG 6. And the idea is that by 2030 we will achieve universal and equitable access to safe water. This is not going to happen. Okay, 2030 is 8 years from now. This is not going to happen. Actually, they showed that in order to achieve these goals, we need to quadruple our efforts. This is also not going to happen. In addition to that, another very important thing that was actually addressed by the UN SDG 6 is that we need also to work bottom up. So not only up bottom from the governments, industry, municipalities, big companies and stuff like that. We need to work with the people, with the communities in order to provide safe water. So this also relates not only on technology, but also on education, on knowledge, on the value of water, and these things. So our objective is to contribute to UN SDG 6. We have collaborators from all around the world. It's open to any IUVA member. And actually, we want to look at UV on the local perspective, okay? And in addition to that, we want to target low middle income countries in order to understand what are the challenges to provide safe water and how UV can contribute to that. So what are we doing? We're doing a series of webinars. We're also in touch with organizations such as the USAID, the World Bank. We're also writing now a white paper. So if any of you want to contribute to our white paper, which will actually target lesson learned, we're also waiting for your contribution.
Yeah, I will say
Now you said it, and it's also recorded.
Yeah, it's recorded, yeah. I only asked for time, that's all.
No, I'm just joking. Don't take me seriously. Okay, so it's a white paper on case studies for using UV in low middle income settings, and we're taking case studies from all around the world, trying to understand what are the challenges in order to use UV. And if you want to get involved, you're always welcome. Please contact us. And this is how I got to know Professor Kanmani. So you can see in the right, okay. And actually, we developed, I would say, a session on implementing UV technologies in low-income middle communities and challenges, which is my passion. And I try to look at publications all across the world to try to seek people that are working with UV in rural areas that are developing technologies that are low cost, that could be implemented in rural settings and maybe peri-urban settings. And then I came across to Professor Kanmani a publication. So I sent her an email. Are you willing to come to Boulder, Colorado, and to present your knowledge in this session? So this was the application in low income communities, and here you are, and here I am now. So this is how things developed and adopted. Okay. So we all know that water has endless dimensions, and I will, in this presentation, really briefly talk about UV in the water and wastewater, maybe if we have time. I'll also present a little bit about UV on surface disinfection, UV on air disinfection, and also my expertise on advanced oxidation processes and how UV can be integrated onto also membranous supports and stuff like that. But it really depends on how. I'll just talk quickly. I think we don't need to talk about this. Let's move on. Just the basis of UV disinfection, okay? So this is the electromagnetic spectrum, and I'm really fascinated about UV. First, it's a physical method. It's not a chemical method. There's no issue with supply chain. If we look at the electromagnetic spectrum, we can see that UV is from the range of the UVC, or the UV that is related to disinfection, is between 200 to 300 nanometer, although the UV is up to 400 nanometers. And it's also in between the visible light range, so the visible is between 400 and 700. So actually we cannot see UV. But if you look at all the manufacturers, UV always looks purple. But UV is not in the visible range, okay? So UV is below the visible range. And how does UV work? So all of us have DNA in our cells. The UV actually is absorbed in the DNA. It results in a dimer, which is called thymine dimer, and it does not allow the microorganisms to replicate. And UV also can come in different wavelengths, especially if we're talking about light-emitting diodes from UV. And this is how UV works. Currently, there are two standard lamps with UV. There's the low-pressure lamp and the medium-pressure lamp. A low pressure are all the small, simple units for water disinfection that you have with a reverse osmosis and a UV lamp. Those small installations are usually low-pressure lamps. And there's also medium-pressure lamps that are mostly used for effluent disinfection, which are polychromatic in source. So you can see that they have actually a very wide spectrum. So as I said, UV is a physical method. The photons are absorbed by the DNA. A dimer is formed, and it actually inhibits replication. And this is, for example, just a picture of a UV mercury lamp. So the traditional lamps are either low pressure, high output, and medium pressure. Each of them have advantages and disadvantages. And today there's also a new type of UV, which is called UV light-emitting diodes, which does not contain mercury, but it also has its advantages and disadvantages in terms of disinfection. Okay? So what are the advantages of LEDs, and why I think that LEDs can actually target disinfection in rural areas where there's issue with supply chain and where there's issues with intermittent water supply, intermittent electricity supply as well. So first, LEDs are compact, they're small, they're instant start-up time, so it's just like turning the light on and off, okay? Where mercury lamps require a warm-up time. If we're talking about systems that are continuous, we don't care about the warm-up time, but if we're talking about systems that the water is intermittent and the water supply is maybe for 2 hours a day, you don't want to waste time on warm-up time, or that people will drink water before the lamp is at its maximum peak electricity. Also, it has multiple inactivation damage mechanisms, which is part of the things that we're working on. And we also patented a technology on how can we use different wavelengths in order to improve the disinfection. However, there are disadvantages. First, a lot of heat is generated, so we have to actually design heat management for these systems, and they have a very low output. Okay. So these are these LEDs. They're cute and small. Very similar to the visible light LEDs that we have in our electrical appliances, right? We have these small red or I don't know, blue or green dots in the electrical appliances. This is very similar, but it's in the UV range, so they emit UV wavelengths. Let's look about the market trend. So we all felt what's happening during the Corona crisis, right? I'm sure we're still not over it, but I kind of feel that we are actually. But during the Corona crisis, UV disinfection has became, I would say, the market increase was tremendous because everyone wanted to disinfect everything. They wanted to disinfect the air that you're breathing, the surfaces that you're touching, the water, everything. And actually, I was approached by so many companies, it was like shocking for me. And that's why I also diversified some of my research to air and surface disinfection. But you can see that in 2025, how the market revenues will increase. So why LEDs are interesting? UV LEDs are interesting because you can actually design LEDs that emit at various wavelengths. So for example, we can see here at 265, 280, 297, whatever. And each wavelength can have a different impact on the microorganisms. So this is very interesting where we can mix and match various wavelengths to have an impact on the disinfection. In addition, one of the really important things with UV reactors is that we need to actually design the reactor correctly, and we need to look also the optical design, the thermal design, the biological testing, and the mechanical. So working with UV, which is a physical technology, we need to actually work on all these aspects in order to disinfect the microorganisms, which is our target. There's also, we can also look at, as I said before, surface disinfection and air disinfection. And UV can also be applied as a direct disinfection technology or indirect by photocatalysis or, as you said, by advanced oxidation. So just by taking a nanocatalyst and exposing it to light, we can induce hydroxy radicals or free radicals that will actually break down contaminants in water and also micropollutants. Okay, so let's just move a little bit about, let's go ahead. When we want to disinfect water, we need to look at an organism that we can actually serve as a surrogate, because we know that sewage contains pathogens, right? Now, it's very difficult to enumerate the pathogens. It's very difficult to count them. Therefore, we're using surrogates to evaluate the technology. So what are we actually doing? We are spiking into our water the surrogate organisms, and we're evaluating them before and after the UV disinfection. Or we can also take, for example, drugs or antibiotics or personal care part, doesn't matter, and we evaluate what happens before and after the technology, okay? And then we can actually look at the effectiveness. Now, MS2 is actually a bacteriophage that can mimic human viruses. It has a capsid surface. In addition to that, it is very resistant. So it's one of the most resistant viruses that are known. We try to understand if we mix and match various UV sources, what will happen. And what we found is something very interesting, that if we actually combine low pressure lamps with LED-based disinfection, we can have a synergy in inactivation of, for example, E. coli, fecalis, and also with wastewater secondary effluents. However, with viruses, we do not see this type of synergy. The addition was more additive. So what we see here is that when we combine different light sources, we increased the inactivation. Now, why is this important? Why is this important? Because if we can have a synergy, which means 1 + 1 equals more than 2. So if we combine two different wavelengths, two different sources, and we get an impact that is more than the sum of each one separately, then definitely we can actually save energy costs. And we know that energy is also carbon and all that stuff. In addition to that, we saw that by combining wavelengths, we can also decrease the photo recovery. So this means that the microbes cannot recover post-disinfection. In addition to that, there are also many other meaningful parameters when designing UV systems. Beyond the wavelength, it's also the intensity. So in the past, many people thought that what you need in order to have efficient disinfection is to control the UV dose. But this is not right, actually. In order to get a certain UV dose, you can increase the exposure time, okay, and lower the intensity, or increase the intensity and lower the exposure time, and multiply these two parameters and have the same dose. So it was thought that if you do that, it doesn't matter how you design your UV reactor. You can either shorten the time, increase the intensity, or decrease the intensity and expose it to a longer time. What you need is the UV dose, right? But it was found wrong, because microbes are actually very complex organisms, and in order to disinfect or inactivate microorganisms, because we don't want to drink them in our water sources, because we know that one of the largest challenges in water supply is safe water, and the biological contamination of water is one of the main reasons for diarrhea and also death of children under the age of 5. So disinfection is something that is very crucial, and to design the disinfection correctly is also something that is actually very much required. So as you know, scientists, we tested the impact of various intensities, various exposure times, and what we saw, something very interesting, is that if we expose the microorganisms to 265 nanometers, it doesn't matter the intensity versus time. What matters is to reach the correct dose. However, when we increase the wavelengths, what we found is that it does matter, that the intensity does matter. And actually, this is something that was very interesting for us. Then we wanted to learn what is the mechanism behind this thing. So just to make it short, we used biosensors. So instead of exposing light to regular organisms, we took E. coli that had a biosensor inside, and whenever it felt stress, it actually luminescent, and that way we could actually understand under which genes are actually induced due to the exposure to UV. And what we found is that when we expose the microorganisms with the biosensor to different wavelengths, the typical 265 nanometer, which is absorbed in the DNA of the microorganism, resulted in the most of the stress. However, we also tested different types of stress, oxidation stress. And what we found is something very interesting, and that was not reported previously in the literature, is that even when we expose microorganisms to UV disinfection, we also induce internal stress in the microorganisms that is related to superoxide radicals, which can also help in the disinfection. So if we take all of this, as like we said before, we as scientists, we can stay in our labs and do whatever, publish papers, stuff like that, and we'll be good. But I believe that as scientists, we really must take the things that we develop into the industry and see how can we actually help technologies and solutions to be better. So what we're doing here is actually we're designing now a UV reactor with multiple wavelengths, but it doesn't only depend on the wavelength, it depends also the intensity, and we're also combining other sources of free radicals that are coming from photocatalysis, and also looking at combining with blue light. So it's a combination of many things. And you would say, like, why blue light? What is very important about blue light? Actually, hospitals, blue light is something very interesting, because blue light by itself is not a disinfectant. However, it can help in maintaining biostatic activity of the water. So it means that if we expose water to a long time under blue light, it can also maintain or reduce or control the regrowth of microorganisms in water tanks. Now, why is this important? Why is this at all important? Because one of the things that happens why water is not safe to drink. So if we look, for example, in many places, water is disinfected and then it's stored in water tank. Now, water that is stored is a ticking bomb. Like, people are not aware of that, but water above 24 hours, if you store it, even if you have a small residual chlorine inside, microorganisms will start to develop and regrowth. Therefore, there is a need to develop smart water storage systems, and this is something that we are also doing. And also, there's also a company that is now collaborating with us on this design to see if we can develop smart water storage systems post UV disinfection. Okay? And again, this is more related to water that is stored maybe more into rural areas. Maybe this problem is not relevant or is not a problem in urban areas, but even water in water tankers or stuff like that, some people don't like the taste of residual chlorine inside the water, and therefore the issue of how can we use light to maintain the biosafety of water is something that is very important. We also are working, but I'll not talk about this today because it's too detailed. We're also working on chemical ways to evaluate how much photons we have in the water with various wavelengths. We've written a review paper that was published just a few months ago on how can we use, for example, ferrioxalate or uridine actinometry in order to evaluate how much UV we have in the water. One of the problems with UV is that regulators say, we don't know how much UV is in the system. Because it's photons, it reacts in nanoseconds. It doesn't stay in the water like chlorine, where you can take a water sample and measure its residual. And therefore, understanding how to measure or how to understand how much UV is in the water is also something that is very important. I'd like to also talk about something that we're now working on. It's an initiative that we call SOLID. And we're also funded by the Asper Foundation, which is one of the largest foundations in Canada. In order to provide safe water in rural areas, I'll just go over this due to lack of time. And the issue is that when we think about technologies, where all of us, or most of us, are engineers, we think technologies will solve the problems of the world. However, this is not the case, because actually the adoption of technologies in various settings is something that is very important. I'll just go over here. So what we're doing, we're developing systems that could be totally off-grid for disinfection of water in rural areas. We already started implementation a few weeks ago, actually in South India, some area. And we're trying to understand what are the challenges, which waters will actually require pre-filtration prior to the UV, which water types require, for example, maybe if we have additional complexities in the water, or for example, iron that absorbs part of the photons, or if we have beyond the disinfection also issues with heavy metals and stuff like that. So we're working on all these aspects of looking at how can we provide safe water. In addition to that, we also developed other technologies to allow disinfection in rural areas and to measure it. So for example, we developed an incubator that cost tens of dollars instead of an incubator that costs $1,000, that people in rural area can actually take a water sample and incubate the water in order to evaluate if the water has microorganisms, so they can be the local point of management for their water. Okay? So these are things that we're working now. Again, due to lack of time, I don't have much time to talk about it, but we did win many competitions, also local and international, for this invention. And again, I think I will just be very briefly, I'll just take 5 more minutes, just talk about UV and advanced oxidation. So advanced oxidation are all the processes that generate hydroxyl-free radicals. They can be combined with nanoparticles in order to induce these reactive species. Again, when we look at AOPs, we need to actually, if it's UV-based AOP, we need to look at all these parameters in order to have an efficient treatment. However, there are many barriers for nanotechnology. There are tons of publications, no applications, or minimal applications. Why is that? Is because you cannot dump nanoparticles into the water. So we need to actually combine them with the support, but we need to do it in an efficient way because we reduce the surface area and all that stuff. We're now working with a project with Fraunhofer Institute on developing smart systems that can be activated by light and be used as a very low-cost system to oxidize micropollutants in water. We're now starting to pilot both in Israel and in Germany, a system that is activated by LEDs and a low-cost system to break down contaminants in water. UV can also be served as surface disinfection. So we can see that we can actually combine different LEDs for surface disinfection. This is a paper that we published on how LEDs can actually inactivate the human coronavirus. We now submitted another paper looking at the different strains, Omicron, Delta, whatever, and see how UV can actually address all the different corona strains that were during this 2.5 years. And maybe just to show you that microbes are everywhere, okay? This is your cell phone. And together with a professor in Northwestern University, we are designing surfaces that are transparent, that with a photocatalyst can be activated by simple light in order to disinfect the systems. But again, lack of time, I'll just go over this quickly. And maybe just the last thing that I want to discuss is that UV LEDs can be integrated also in disinfection of various areas. And last thing, this is really the last thing, UV with air disinfection. So UV can also be used by air disinfection. We were actually approached by one of the largest HVAC companies in Israel, telling us, develop a system that will use UV to disinfect air. At first I said, no, I'm a water person, I'm not going to work on air. I mean, surfaces is okay, but air is totally not my area. I'm not going to do this. But at some point I said, okay, this really sounds interesting, because actually the human coronavirus is in an aerosol, and an aerosol is actually saliva, it's liquid. So, but it does have different thought processes. It's not the same as disinfecting water because it has its complexities. So the ASHRAE, which is the largest organization for HVAC systems, actually said that one of the ways to control human coronavirus is by disinfection, and one of the disinfection that is most effective against it is UV. And UV can be integrated in various ways, but one thing is very important is that it has to be safe. It has to be contained. We as humans cannot get exposed directly to UV because we also have DNA, and our DNA will also absorb the UV. So therefore, one of the issues is that many products were there in the market which were not safe and actually dangerous. So what we're doing is we are actually developing UV systems that will be used to disinfect air ducts. We are using different viruses. We are looking at the guidelines, the international standards. And again, one of the complexities is saliva. Saliva is not like water. It has high absorbance, also around 280 nanometers, which will interfere with UV disinfection. And in addition to that, we need to generate the aerosols because we built a lab actually. It took us a full year to build a lab that actually releases aerosols with viruses through an air duct, which we expose it to UV, and then we need to measure the viruses inside the aerosols, and that by itself took months of us for develop. How can we recover the viruses from the aerosols from these systems? And that's it. I would like to thank you, and I hope it didn't take, I hope it was okay with timing, and thank you very much.